Something is broadcasting from deep space with power that defies physics. These signals release more energy in a single millisecond than our sun produces in an entire year, then vanish without warning. For decades, astronomers dismissed them as equipment malfunctions. They were wrong. On March 16, 2025, telescopes detected the brightest radio flash ever recorded. Scientists nicknamed it RBFLOAT, the radio brightest flash of all time. What they found when they traced it back will change how we understand the universe. The cosmos isn't quiet. It's screaming. Radio waves flood through space constantly, most of them predictable, documented, understood. Background radiation from the Big Bang hums at a steady frequency. Pulsars spin like cosmic lighthouses, broadcasting their signals with clockwork precision. We've mapped these sounds, cataloged their sources, built entire models of galactic structure around their behavior. Then in 2007, something different appeared. A graduate student named Duncan Lorimer was sifting through archived data from the Parkes Observatory in Australia, looking at recordings nobody had bothered to examine closely. Buried in 6 years of observations sat a signal lasting just 5 milliseconds. 5/1000ths of a second. The energy signature suggested it had traveled across 3 billion light-years before reaching Earth. One signal. 5 milliseconds. 3 billion light-years. The team ran every test they could imagine. Equipment malfunction. The telescope had been working perfectly. Terrestrial interference. The signal's dispersion pattern proved it came from deep space. Human error. Multiple independent analyses confirmed the same result. This wasn't supposed to exist. The physics didn't make sense. No known astronomical object could generate that much power in such a brief burst. The paper describing the discovery used careful, measured language, but the implication was unavoidable. We'd found something completely new. They called it a fast radio burst. The name sounds almost boring, technical, safe. It masks the profound strangeness of what these signals represent. For years, that single detection stood alone. Critics suggested it might be a fluke, a cosmic one-off, perhaps even contamination in the data despite all evidence to the contrary. Astronomers searched for more, aiming telescopes at the same patch of sky, scanning other regions, upgrading their detection equipment. Nothing. Then they started finding dozens. Then hundreds. Then thousands. The CHIME telescope in British Columbia changed everything. Picture 4 enormous metal half-pipes, each 100 meters long, arranged in a row like a giant skateboard ramp. No moving parts. It just stares straight up, watching the sky rotate overhead. Within 3 weeks of testing in 2018, still not fully operational, CHIME caught 13 fast radio bursts. We weren't looking hard enough before. These signals aren't rare. They're everywhere. Current estimates suggest a fast radio burst occurs somewhere in the observable universe roughly once every minute. Most pass through our cosmic neighborhood undetected. We see only the tiny fraction that happens to point directly at Earth, and only when our telescopes are looking in exactly the right direction at exactly the right microsecond. The math gets disturbing when you extend it outward. If our small slice of sky catches this many, how many are we missing? How many are happening in regions we can't observe, at frequencies we can't detect, or simply while we're looking the wrong way? But here's what really keeps astronomers awake at night. We still don't know what causes them. 47 different theories currently attempt to explain fast radio bursts. 47. That's not a sign of scientific consensus. That's a sign we're grasping at straws. The list includes neutron star collisions, white dwarf mergers, lightning on pulsar surfaces, collapsing cosmic strings, and yes, even alien spacecraft propulsion systems. Most of those theories are probably wrong. Maybe all of them are. What we do know creates more questions than answers. Fast radio bursts are incredibly distant, most originating in galaxies billions of light-years away. They're extraordinarily brief, typically lasting between 1 and 10 milliseconds. They're immensely powerful, some outputting 500 million times the energy of our sun in less time than it takes to blink. And they're getting stranger. In 2020, astronomers detected a fast radio burst from inside our own galaxy. Not billions of light-years away. 30,000 light-years. Practically next door in cosmic terms. The source? A magnetar called SGR 1935 plus 2154. Magnetars are neutron stars, the collapsed cores of dead massive stars, compressed so densely that a teaspoon of their material would weigh 1 billion tons on Earth. They spin multiple times per second despite being 12 miles across. Their magnetic fields are the strongest in the universe, a quadrillion times more powerful than Earth's. These are places where physics operates at its absolute limit. The surface of a magnetar is hell on a scale we can barely conceptualize. Gravity so intense it warps spacetime. Magnetic field strong enough to disintegrate atoms. Surface temperatures exceeding 10 million degrees. And occasionally, something goes wrong. The interior of a magnetar exists as a superfluid, matter in a state that doesn't exist anywhere on Earth. Sometimes this superfluid sloshes against the solid crust like water in a spinning bowl. When that happens, the crust can crack. Material from the interior erupts into space. The star's rotation suddenly slows. And it screams in radio waves. NASA's NICER telescope on the International Space Station and the NuSTAR satellite caught one of these events in October 2022. They watched the magnetar for hours before the burst, capturing X-ray eruptions and gamma-ray flares building up to the main event. Then the fast radio burst exploded outward. They kept watching afterward, seeing the aftermath, the cooling, the gradual return to normal. For the first time, we saw what happens before and after. The picture emerging is violent beyond imagination. The burst likely originated from the magnetosphere, the magnetic field surrounding the neutron star. In that region, magnetic field lines twist and snap like overstressed cables. Particles accelerate to nearly light speed. Temperatures spike to billions of degrees in microseconds. Radio waves amplify and focus into a beam so intense it can cross intergalactic space and still register on our instruments. This explains some fast radio bursts. Not all of them. In 2024, astronomers traced a fast radio burst to the outskirts of a dead elliptical galaxy. No new stars forming. No young magnetars. No obvious energy source. The burst came from a region 130,000 light-years from the galaxy's center, in the cosmic equivalent of empty desert. How do you get an energetic explosion in a place with no fuel? That's the question nobody can answer yet. The discovery shattered the assumption that all fast radio bursts need young, active stellar environments. Some clearly do. Others apparently don't. We're missing something fundamental. Then there's the repeaters. Most fast radio bursts appear once and never again. You see the flash, you trace it back to a distant galaxy if you're lucky, and that's it. Story over. But roughly 3% of detected bursts repeat. Same source. Multiple flashes over days, weeks, or months. One repeating source follows a 16-day cycle. For 4 days, it bursts multiple times per hour. Then silence for 12 days. Then the pattern starts again. Like clockwork. No deviation. What kind of cosmic mechanism keeps such precise time? Orbital dynamics. Precession. Tidal forces from a companion object. We're speculating. The honest answer is we don't know. Another repeating source, designated ESCAP J 1935 plus 2148, pulses every 53.8 minutes. Not seconds like a pulsar. Minutes. That timing places it in what astronomers call the pulsar death valley, a theoretical zone where radio emission shouldn't be possible. The physics that allows pulsars to broadcast requires fast rotation. This thing spins far too slowly. It should be silent. It isn't. The strangest object might be ESCAP J 1832-0911, located 15,000 light-years away in our own galaxy. Every 44 minutes, it flashes in both radio waves and X-rays simultaneously for 2 minutes. 2 minutes is an eternity compared to typical fast radio burst timescales. And the dual wavelength emission suggests something completely different is happening. We've also found odd radio circles. Gigantic structures hundreds of thousands of light-years across, visible only in radio frequencies, shaped like perfect rings. Their edges glow brighter than their centers. They don't match any known type of astronomical object. Current theories suggest they might be shock waves from supermassive black holes, or galactic superwinds, or vortex bubbles in space itself. Or something else entirely. The technology hunting these signals has evolved dramatically. The CHIME outrigger array extends the main telescope's capabilities by adding smaller stations in California and West Virginia. Together, they use very long baseline interferometry, combining signals from telescopes separated by thousands of miles to achieve precision comparable to spotting a guitar pick from 1,000 kilometers away. That precision located RBFLOAT, the brightest fast radio burst ever detected. The signal came from galaxy NGC 4141, 130 million light-years distant. Follow-up observations with the James Webb Space Telescope found a faint infrared source at the exact location. Not a galaxy. Not a star. Something small, compact, and incredibly energetic. The breakthrough revealed the burst originated from a region only 45 light-years across. Smaller than the typical size of a star cluster. For context, the nearest star to our Sun sits 4 light-years away. This region could contain just a handful of objects. Australian astronomers developed Krakow, a system that detects and analyzes cosmic radio flashes in real time. Traditional methods record everything and analyze later. Krakow processes data instantly, identifying transient signals as they happen. During its pilot run, it caught 2 fast radio bursts, identified 2 sporadically emitting neutron stars, refined the positions of 4 pulsars, and detected 20 additional bursts in subsequent observations. We're getting better at catching these signals. We're getting better at pinpointing their sources. We're collecting data at unprecedented rates. We're still nowhere close to understanding what they really are. Some fast radio bursts carry information beyond just their existence. The radio waves arrive slightly dispersed, different frequencies reaching us at fractionally different times. That dispersion reveals how much ionized material the signal passed through on its journey. By measuring that precisely, we can map the invisible matter between galaxies. Most of the universe's ordinary matter, the protons and neutrons that make up atoms, isn't in stars or planets. It's scattered through intergalactic space in diffuse clouds so thin we can barely detect them. Fast radio bursts illuminate these clouds like flashlights in fog. Each burst traces a line through space, measuring density, temperature, composition. They've become scientific tools despite remaining scientific mysteries. But the question everyone wants answered, the question that underlies every observation and every theory, remains unanswered. What creates signals this powerful? Magnetars provide our strongest lead. Neutron stars already occupy the extreme end of physics. A typical neutron star packs more mass than our Sun into a sphere 20 kilometers across. Gravity compresses matter so intensely that electrons merge with protons, creating a substance made almost entirely of neutrons. A teaspoon of this material would weigh 1 billion tons on Earth. The surface gravity exceeds Earth's by 200 billion times. Magnetars take this extremity further. Their magnetic fields reach quadrillions of times stronger than Earth's field. Strong enough to distort the atomic structure of empty space itself. Strong enough to be lethal at a distance of 1,000 kilometers. The field contains more energy than our Sun emits in 100,000 years. These objects spin. Not slowly. SGR 1935 plus 2154, the magnetar inside our galaxy that produced a detectable fast radio burst, rotates 3.2 times per second. Its surface moves at 7,000 miles per hour. The combination of density, gravity, rotation, and magnetic intensity creates conditions we can barely model with our current physics. The exterior of a magnetar forms a crystalline lattice of iron nuclei, harder than diamond yet constantly stressed by forces that would vaporize any normal material. Beneath that crust lies something stranger. The interior pressure forces neutrons into a superfluid state. No viscosity. No friction. Flowing without resistance. Think of a spinning fishbowl filled with water. The bowl rotates. The water inside rotates. But they don't always stay synchronized. The water can slosh, creating internal currents that move independently of the container. Inside a magnetar, when the superfluid interior and the solid crust fall out of sync, the fluid transfers enormous energy to the outer layers. That transfer can crack the surface. When the crust fractures, it releases stored magnetic energy in a violent reorganization. Material from the interior might erupt outward. The star's rotation rate changes abruptly as angular momentum redistributes. We've observed these starquakes in X-ray emissions. Sudden brightening followed by a gradual decline. The magnetar spinning slightly slower afterward. But here's what makes the connection to fast radio bursts compelling. In October 2022, two NASA X-ray telescopes watched SGR 1935 plus 2154 for hours. NICER, mounted on the International Space Station. New star, in low Earth orbit. Both instruments captured X-ray activity before and after the magnetar produced a fast radio burst. The magnetar released eruptions of X-rays and gamma rays. Then the radio burst. Then more high-energy emissions. The sequence suggested a direct physical connection between the surface disruption and the radio signal. The burst itself likely emerged from the magnetosphere, the region immediately surrounding the star where magnetic fields dominate. Material ejected from the surface moves through this zone at relativistic speeds, creating shock waves in the magnetized plasma. Those shocks could generate coherent radio emission through processes we're still working to understand. The distance matters. Researchers estimate FRB 20221022A originated less than 10,000 kilometers from the neutron star's surface. Less than the distance between New York and Singapore. For context, our moon orbits Earth at 380,000 kilometers. This proximity places the emission region inside an environment where magnetic fields reach the physical limits the universe permits. Some physicists questioned whether radio waves could even escape from such extreme plasma conditions. The density of charged particles, the field strength, the energy levels involved. Standard models suggested the radio emission should be absorbed or scattered before reaching space. It wasn't. That tells us something important about the physics we don't yet understand. The emission mechanism must be extraordinarily efficient. Or it operates through processes we haven't identified. Or both. April 2020 marked the turning point. Astronomers detected a fast radio burst from SGR 1935 plus 2154, 30,000 light-years away in the Vulpecula constellation. The first FRB detected inside the Milky Way. The first traced to a known source. The event strongly supported magnetars as the origin, but it simultaneously revealed how much we still don't know. Not every magnetar produces detectable radio bursts. We've observed hundreds of X-ray flares from various magnetars. Only a handful generated radio signals. What determines whether a particular eruption creates a fast radio burst? We don't know. Is it the angle? The magnetic field configuration? The amount of material ejected? The rotation rate at that moment? And magnetars don't explain everything. FRB 20240209A appeared in the outskirts of an ancient elliptical galaxy, 130,000 light-years from the galactic center. Dead galaxies don't form new stars. They don't have the stellar nurseries where young, active stars typically reside. Magnetars are thought to form from massive stars that died recently. This FRB location contradicts that expectation. Either magnetars can persist far longer than our models predict, remaining capable of producing bursts billions of years after formation. Or some fast radio bursts originate from different sources entirely. Merging neutron stars. White dwarf collisions. Phenomena we haven't imagined yet. The repeating bursts complicate the picture further. FRB 180916.J0158 plus 65 follows a 16-day cycle. For days of regular activity, transmitting radio bursts almost hourly. Then 12 days of silence. Then the pattern repeats. This periodicity suggests orbital mechanics. Perhaps a neutron star orbiting a companion. The geometry changes. Sometimes conditions favor radio emission. Sometimes they don't. But most fast radio bursts don't repeat. Or they haven't repeated in our observations. RBFLOAT, the brightest burst ever detected, came from NGC 4141. Astronomers examined more than 6 years of CHIME data covering that region. Hundreds of hours of observation. No additional signals. Does that mean it won't repeat? Or that it repeats on timescales longer than we've been watching? Or that it was a one-time catastrophic event? Consider the energy requirements. Sun bursts release as much energy in milliseconds as our sun emits in an entire year. That's not a casual emission. something violent is happening. Something that involves massive amounts of matter moving at relativistic speeds. Something that converts gravitational or magnetic energy into coherent radio waves with shocking efficiency. The dispersion measurements add another layer. Radio waves traveling through ionized plasma get slowed down slightly. Higher frequencies travel faster than lower frequencies. By the time the signal reaches Earth, the different frequencies arrive at fractionally different times. We can measure that delay with extreme precision. That dispersion tells us how much ionized material the signal passed through. More dispersion means more electrons encountered along the path. By measuring bursts from known distances, we can calibrate the relationship between dispersion and distance. Then we can use new bursts to estimate how far they traveled. This transforms fast radio bursts into cosmological tools. Most of a universe's ordinary matter isn't in stars or planets or gas clouds we can see. It's scattered through intergalactic space in diffuse plasma so thin it's nearly impossible to detect directly. But fast radio bursts illuminate it. Each signal traces a line through space, sampling the density, temperature, and composition of the intergalactic medium. Early results already confirm that much of the missing matter resides in this diffuse state. The measurements matched theoretical predictions about how matter distributed itself after the Big Bang. We're using mysterious signals from unknown sources to map the invisible structure of the universe. The technology continues advancing. Very long baseline interferometry combines signals from telescopes separated by thousands of miles. The effective resolution becomes equivalent to a telescope as large as the separation between instruments. That's how we achieve precision comparable to spotting a guitar pick from 1,000 kilometers away. Krakow processes data in real time. Traditional methods record everything, analyze later. Krakow identifies transient signals as they happen, immediately triggering follow-up observations with other instruments. During its pilot run, it caught bursts, located neutron stars, refined pulsar positions, and proved that instant analysis opens new observational possibilities. The James Webb Space Telescope entered the investigation. After RBFLOAT was detected, Webb pointed at the source location. Infrared observations revealed a faint signal. Not a galaxy. Not a star. Something compact. Something emitting at wavelengths invisible to optical telescopes. The follow-up narrowed the source region to 45 light-years across. Still large by terrestrial standards. Tiny by astronomical scales. You're watching physics operate at its absolute limits. Magnetic fields stronger than anything achievable in laboratories. Densities that compress nuclei into exotic states of matter. Rotation speeds approaching the threshold where centrifugal force would tear the object apart. Temperatures measuring billions of degrees. Gravity warping spacetime into configurations we can barely calculate. And somehow, in these environments where our understanding of physics gets tested beyond conventional boundaries, nature produces radio signals so powerful they cross intergalactic distances and still arrive strong enough to detect. Signals that last milliseconds yet carry information about the structure of the universe. Signals that simultaneously represent our greatest mystery and our newest scientific instrument. But we haven't addressed the signal everyone wants to know about. The one that captured public imagination decades before fast radio bursts were discovered. The one that still has no explanation. August 15, 1977. Ohio State University's Big Ear radio telescope was conducting its routine scan of the sky, searching for something humanity had never found. The equipment recorded everything automatically. Data printed onto continuous paper. Nobody watched in real time. The telescope listened. The computers logged. Days later, astronomer Jerry Emmons sat down to review the printouts. He was looking for anomalies, unusual patterns, anything that didn't match the background hiss of the universe. Then he saw it. 6 characters. 6 alphanumeric values that represented signal intensity far beyond anything the telescope normally detected. The sequence read 6EQUJ5. Each character corresponded to a specific intensity level. The system used numbers 0 through 9, then letters A through Z for higher values. Normal background noise registered around 1 or 2. This signal peaked at U. Intensity 30. 30 standard deviations above background noise. Emmons grabbed a red pen. He circled the sequence. In the margin, he wrote one word. Wow. The signal lasted exactly 72 seconds. Not because it stopped transmitting. Because that's how long Big Ear could observe any given point in the sky. The telescope used Earth's rotation to scan. As the planet turned, different regions of space drifted through the receiver's field of view. Each source got 72 seconds of observation time. Maximum. The WOW signal filled that entire window. It appeared. It peaked. It faded. It vanished. Here's what made it extraordinary. The signal was narrowband. Extremely narrow. Centered at 1420 MHz. That frequency sits right in the middle of the hydrogen line, a region of the radio spectrum considered so important for potential interstellar communication that international agreement prohibits terrestrial transmissions there. It's the cosmic equivalent of a quiet zone. The bandwidth was tight, focused, deliberate looking. Natural cosmic sources typically produce broadband emissions. They spray radio energy across wide frequency ranges. This signal occupied a razor-thin slice of spectrum. The kind of precision you'd expect from an engineered transmitter. The signal's intensity rose and fell in a pattern matching exactly what you'd predict from a source passing through the telescope's beam. As Earth rotated, the antenna's sensitivity peaked when the source aligned perfectly, then declined as it drifted away. The shape of that rise and fall matched theoretical predictions. The direction? Constellation Sagittarius. Specifically, a region northwest of the globular cluster M55. No stars there bright enough to have cataloged names. No obvious targets. Just empty-looking space between the recognizable landmarks. What happened next tells you everything about how science approaches extraordinary claims. They looked again. The Big Ear telescope had 2 receivers pointed at slightly different parts of the sky. If a signal came from space, both receivers should have detected it with a 3-minute delay as Earth's rotation carried the second receiver through the same region. The second receiver detected nothing. 0. Background noise. That created immediate doubt. A genuine cosmic source should have appeared twice. It didn't. Maybe equipment malfunction. Maybe terrestrial interference that happened to align perfectly with the observation window. Maybe something else entirely. They kept searching. Big Ear continued scanning that region whenever it rotated back into view. Nothing. Months passed. Years passed. Decades passed. The signal never repeated. Other telescopes joined the search. More sensitive instruments. Wider frequency coverage. Different locations on Earth. None found anything resembling the WOW signal coming from that direction. 47 years later, we still have no explanation. Let's examine the possibilities. Equipment malfunction ranks high on the list. Telescopes are complex machines. Electronics fail. Connections corrode. Cosmic rays strike semiconductors. A single bit error in the right place could create a false detection. But the signal's characteristics argue against simple malfunction. The rise and fall pattern matched predictions too precisely. Random noise doesn't organize itself that neatly. Terrestrial interference is another candidate. Aircraft. Satellites. Secret military transmissions. Ground-based radio sources reflecting off something in the atmosphere. The problem? The signal came from a protected frequency. The hydrogen line. International regulations ban transmissions there specifically to keep it clear for astronomical observations. Would someone violate that ban? Possibly. Would they do it with such precise frequency control that it mimicked an astronomical source? Less likely. Could it have been a satellite passing through the beam? Satellites move. They drift across the sky. As they move, the Doppler effect shifts their frequency. A satellite passing through Big Ear's field of view should have shown frequency drift. The WOW signal showed none. The frequency remained stable throughout the observation. There's a hypothesis involving comets. In 2015, astronomer Antonio Perez suggested that comets surrounded by hydrogen clouds could produce signals at the hydrogen line frequency. He identified 2 comets that were in the general vicinity in 1977, though their positions weren't precisely catalogued at the time. Later observations of similar comets showed they do emit at hydrogen frequencies. Weakly. Very weakly. Could a comet produce a signal 30 times stronger than background noise? The astronomical community remains skeptical. The intensity seems wrong. The duration seems wrong. The sharpness of the frequency seems wrong. But it's not impossible. Then there's the explanation nobody wants to say out loud in professional settings, but everyone thinks about. What if it was exactly what it looked like? A deliberate transmission. A beacon. A signal meant to be found. The frequency choice supports this. Hydrogen is the most abundant element in the universe. Any technological civilization would know about the hydrogen line. It's a universal landmark in the radio spectrum. Choosing that frequency for interstellar communication makes logical sense. It's where everyone would think to listen. The narrowband nature supports it. Natural processes produce messy signals. Technology produces clean ones. This was clean. The 72-second duration is harder to interpret. Maybe that's how long they transmit it. Maybe their beam swept across our location like a lighthouse. Maybe Earth's rotation carried us out of alignment before the transmission ended. We have no way to know. What we do know is that statistical analysis of the signal reveals nothing impossible. The intensity, the frequency, the duration all fall within the range of what a powerful radio transmitter could produce. Not a transmitter using technology beyond our understanding. A transmitter using principles we already know. Just bigger. More powerful. pointed in our direction at the exact moment we happened to be listening to that exact patch of sky. The probability of that alignment seems impossibly small. Unless someone wanted to be heard. Unless the transmission wasn't a brief test but a continuous broadcast we briefly intersected. Unless there are thousands of these signals crisscrossing the galaxy and we finally caught one. The search for extraterrestrial intelligence continues. Modern programs like Breakthrough Listen scan millions of stars across billions of frequency channels. They've detected nothing comparable to the WOW signal. Thousands of candidate signals have been identified, all explained as interference or instrumental effects. All except one. What makes the WOW signal different from fast radio bursts? Intention. FRBs are clearly natural phenomena. Magnetars. Neutron stars. Extreme astrophysical processes. The physics makes sense even if the details remain unclear. The WOW signal's physics makes sense too. But the characteristics align too perfectly with what we design if we wanted to send a message across interstellar space. That alignment might be coincidence. Might be human pattern recognition finding meaning in randomness. Might be our desire to not be alone in the universe coloring our interpretation. Or might be exactly what it appeared to be. A signal. From someone. Somewhere. Saying hello. We'll probably never know. The source never repeated. The equipment that detected it no longer exists. Big Ear was dismantled in 1997 to make room for a golf course. The exact location in space has been scanned repeatedly by more sensitive instruments. Nothing. Silence. Whatever produced that signal either stopped transmitting, moved, or never existed in the way we interpret it. But on August 15, 1977, for exactly 72 seconds, something in the direction of Sagittarius produced a radio signal that looked precisely like what we'd expect from an attempt at interstellar communication. That fact remains unexplained, unrepeated, unforgettable. And while we search for answers to mysteries like the WOW signal, other strange radio phenomena continue emerging from completely unexpected places, challenging everything we thought we understood about what the universe can produce. The center of our own galaxy has been broadcasting something equally bizarre. ASCAP J1736008.2-321635. A mouthful of a designation for a signal that refuses to follow any known pattern. Discovered in early 2022 using the Australian Square Kilometre Array Pathfinder, this source beams radio waves from the galactic center in ways that make no astrophysical sense. The signal turns on. Stays on for weeks. Turns off. The brightness changes dramatically, sometimes declining in a single day. Then it returns, brighter than before, following no predictable schedule. What makes this genuinely strange is polarization. Radio signals from natural sources are typically unpolarized or weakly polarized. This source is highly polarized. In observations capturing thousands of radio sources, only about 10 show this characteristic. This one is among them. The location doesn't help. The galactic center is crowded. Dense with stars, gas clouds, magnetic fields, and a supermassive black hole. Identifying the exact source becomes nearly impossible. Optical telescopes see nothing at that position. X-ray telescopes detect nothing. Whatever produces this signal exists only in radio wavelengths. It shares similarities with galactic center radio transients, another class of mysterious sources detected near the galactic center. They turn on and off irregularly. They're highly polarized. They show up in radio but nowhere else in the electromagnetic spectrum. We've cataloged a few. We understand none of them. The prevailing theories all have problems. Maybe it's a pulsar with an unusual rotation period. But pulsars don't typically turn off for weeks then suddenly reactivate. Maybe it's a magnetar. But magnetars produce X-rays and gamma rays. This doesn't. Maybe it's a binary system where one star periodically eclipses the radio emission. But the timing doesn't match orbital mechanics. Here's what frustrates astronomers. The signal is clearly real. Multiple observations confirm it. The equipment functions correctly. The data processing is sound. Something at the galactic center produces polarized radio waves on an irregular schedule. That something just doesn't match any known category of astronomical object. The universe apparently contains more variety than our models predict. Which brings us to objects so strange they needed an entirely new classification. Odd radio circles. ORCs. Discovered accidentally in 2019 during a survey of the radio sky, these structures look exactly like their name suggests. Perfect circles. Faint. Visible only in radio wavelengths. Each one spanning hundreds of thousands of light years. The first discovery seemed like a mistake. A processing error. Circular artifacts appear sometimes in radio astronomy data. But this circle appeared in multiple independent observations. Then another circle appeared. Then another. For distinct ORCs identified in the initial survey. They share specific characteristics. Roughly circular shape. Brighter along the edges. Completely invisible in optical, infrared, and X-ray observations. Located away from the galactic plane. Each approximately 1 arcminute across. That size is deceptive. 1 arcminute doesn't sound large. But these circles are distant. Extremely distant. The angular size translates to physical structures spanning distances that dwarf entire galaxies. We're looking at phenomena operating on scales that challenge comprehension. What produces a perfect radio circle 500,000 light-years across? The theories reveal how little we understand. Maybe they're shock waves from supermassive black holes. Galactic superwinds. Jet deflections. Vortex bubbles in space. Each explanation requires extreme physics. Each has problems explaining the observations. The shock wave theory seems promising. Supermassive black holes occasionally explode outward, ejecting material at tremendous velocities. This material could create expanding spheres of magnetized plasma. From our perspective, we'd see a circle. The edge would be brighter because we're looking through more material along the rim. But shock waves typically fade as they expand. These ORCs remain visible despite their enormous size. Whatever maintains their structure operates over timescales of millions of years. That requires sustained energy input. From what source? The vortex bubble theory gets stranger. Certain cosmological models predict that spacetime itself could form bubble-like structures under extreme conditions. These bubbles would trap magnetic fields. The fields would emit radio waves. We'd see circles. This explanation requires physics beyond our current understanding. It predicts effects we've never observed. It suggests the universe contains structures formed during its earliest moments, now billions of light-years across, just becoming visible. Maybe ORCs represent the same phenomenon at different evolutionary stages. Maybe we're seeing spheres from different angles. Maybe each one has a unique origin and they're not actually related at all. What we know is this: 4 confirmed ORCs exist. Possibly more awaiting discovery. Each one is a mystery wrapped in radio emission. Each one suggests processes operating on scales where our intuition fails completely. And while we puzzle over giant circles, another class of signals emerged that changed everything we thought about timing. Long-period radio transients. Objects that flash in radio wavelengths on timescales measured in minutes. Not milliseconds like fast radio bursts. Not seconds like pulsars. Minutes. ASCAP J 1832-0911 was the first. Located within the Milky Way about 15,000 light-years away. It flashes for 2 minutes. Then goes silent. Exactly 44 minutes later, it flashes again. This pattern continues indefinitely. The periodicity is the problem. Neutron stars rotate quickly. Seconds or fractions of seconds. White dwarfs rotate more slowly but still complete rotations in minutes at most. Nothing in our models produces a regular pulse every 44 minutes. Then ASCAP J 1935 plus 2148 appeared. Same pattern. Different period. This one flashes every 53.8 minutes. The longest period ever recorded for such a phenomenon. That period places it in what astronomers call the pulsar death valley. The region where neutron stars shouldn't produce detectable radio signals. Their rotation is too slow. The mechanism that generates beams of radio emission requires faster spin rates. Below certain thresholds, the beams shut off. These objects sit well below those thresholds. Yet they beam. Regularly. Predictably. Here's what makes them genuinely bizarre. They emit in multiple wavelengths. Radio and X-rays simultaneously. That combination suggests extremely strong magnetic fields. Magnetar strength fields. But magnetars are young neutron stars. These signals come from objects that should be old. Cold. Magnetically dead. Unless our understanding of neutron star evolution is incomplete. Unless certain neutron stars can maintain strong magnetic fields far longer than predicted. Unless there's a mechanism we haven't discovered that reactivates magnetic fields in old neutron stars. Or maybe they're not neutron stars at all. White dwarfs can have magnetic fields. Not as strong as neutron stars, but strong enough to produce radio emission under the right conditions. If a white dwarf is part of a binary system, material falling onto its surface could trigger periodic outbursts. But that doesn't explain the X-rays, or the precise timing, or the fact that no optical companion has been detected near either source. The current hypothesis involves a neutron star and a white dwarf orbiting each other. Every 54 minutes, they align. The neutron star's magnetic field interacts with material from the white dwarf. This interaction produces both radio waves and X-rays. Then the alignment ends. The signal stops. 44 or 54 minutes later, the cycle repeats. This explains some observations. Not all of them. The energy budget doesn't quite work. The emission mechanism remains unclear. The lack of any detected companion is problematic. What we're seeing is either a new class of object or a known class behaving in ways we didn't think possible. Either option requires rewriting parts of stellar physics. The universe keeps presenting us with signals that don't fit. Each discovery narrows the possibilities. Each observation adds constraints. Eventually, the constraints will force the correct explanation into view. Until then, we catalog. We measure. We build better detectors. Speaking of better detectors, the technology for finding these signals has evolved dramatically. CHIME changed everything. The Canadian Hydrogen Intensity Mapping Experiment. For enormous parabolic troughs in British Columbia, each 100 meters long, fixed in place, pointing straight up. Most radio telescopes move. They track objects across the sky. CHIME doesn't move. It lets the sky move. As Earth rotates, different regions pass through CHIME's field of view. In 24 hours, it scans the entire visible sky. The design seems counterintuitive. Why build a telescope that can't point? Because pointing takes time. Moving a massive dish is slow. Repositioning loses observing time. CHIME eliminates that problem entirely. It observes everything. Always. The data volume is staggering. CHIME generates terabytes of data every day. Processing that volume requires specialized computers, custom algorithms, real-time analysis that can identify interesting signals buried in noise. The payoff has been extraordinary. Since becoming operational in 2017, CHIME has detected thousands of fast radio bursts. More than all previous telescopes combined. It's found repeating sources, non-repeating sources, bursts from nearby galaxies, bursts from distant ones. The CHIME outrigger array extends this capability. Smaller versions of the main telescope installed in California and West Virginia. Together with CHIME, they form a very long baseline interferometry network. The separation between telescopes allows precise localization. When all three detect the same burst, triangulation narrows the source position dramatically. Instead of knowing a burst came from somewhere in a region the size of the full moon, we know it came from a spot smaller than a star cluster. That precision enabled the discovery of RBFLOAT, the brightest fast radio burst ever detected. Traced to galaxy NGC 4141, 130 million light-years away. The localization was so precise that follow-up observations with the James Webb Space Telescope detected a faint infrared signal at the exact same location. For the first time, we're seeing not just the burst but its environment. The region where it formed. The galaxy where it originated. The context that might finally explain what produces these signals. The technology keeps improving. Krakow, developed by an Australian team, detects cosmic flashes in real time. Previous systems recorded everything and analyzed later. Krakow analyzes as it observes. When it detects something interesting, it immediately triggers follow-up observations. This capability is critical because these signals don't wait. They appear. They vanish. If you're not watching at the exact moment, you miss them. Real-time detection means you can catch them while they're still active. Point other telescopes at the same location. Capture data across multiple wavelengths simultaneously. Each technological advance reveals new mysteries while solving old ones. The scientific value extends far beyond identifying sources. These signals are becoming tools for measuring the universe itself. Think about what happens when a fast radio burst travels through space. It doesn't move through a perfect vacuum. Between galaxies exists something called the intergalactic medium. Diffuse ionized gas. Electrons scattered across vast distances. Invisible to most observation methods. When radio waves pass through this medium, they interact with free electrons. The interaction causes dispersion. Different frequencies travel at slightly different speeds. By the time the signal reaches Earth, lower frequencies arrive slightly later than higher frequencies. The delay is measurable, precise, and it tells us something fundamental about everything the signal passed through. The degree of dispersion depends on electron density along the path. More electrons create more delay. Fewer electrons create less. By measuring the dispersion precisely, astronomers can calculate the total number of electrons between the source and Earth. This measurement reveals the density of matter in intergalactic space. Why does that matter? Because there's a cosmic accounting problem. When astronomers add up all the visible matter in the universe, stars, galaxies, gas clouds, the total falls short. The amount predicted by Big Bang models doesn't match what we observe. About half of the expected ordinary matter is missing. Not dark matter. Regular protons and neutrons. Just not where we expected them. The leading theory suggests this missing matter exists in the intergalactic medium. Too diffuse to observe directly. Too spread out to form detectable structures. Fast radio bursts offer a way to test this hypothesis. Each burst that travels through intergalactic space carries information about electron density. Enough bursts from enough distances create a map. A three-dimensional picture of matter distribution across cosmic scales. Early results support the missing matter hypothesis. FRB dispersion measurements align with predictions that much of the universe's ordinary matter resides between galaxies. The signals are confirming theoretical models. Solving cosmological puzzles. Transforming from mysterious phenomena into precision measurement tools. There's another application. Cosmology itself. The expansion rate of the universe. The value of the Hubble constant. There's currently a tension between different measurement methods. Observations of the early universe suggest one expansion rate. Local measurements suggest a slightly different rate. The discrepancy is small but statistically significant. It might indicate new physics. Or it might indicate systematic errors in one method. Fast radio bursts could provide an independent measurement. The relationship between distance and dispersion depends on the expansion history of the universe. With enough FRBs at known distances, astronomers could measure cosmic expansion independently of other methods. A third data point to resolve the tension. But that requires knowing distances precisely. Which brings us back to localization. You need to identify the host galaxy. Measure its redshift. Confirm the FRB originated there. The CHIME outriggers enable this. So do other new instruments. Meerkat in South Africa. ASCAP in Australia. Each adds capability. Each improves precision. The global network is growing. Telescopes on multiple continents. Different observation strategies. Some scan wide areas. Others follow up detections with targeted observations. The combination maximizes discovery while enabling detailed study of individual events. Now consider the repeating sources. They present unique opportunities and unique challenges. FRB 180916 repeats on a 16-day cycle. For days of activity, 12 days of silence. The pattern is regular, predictable, which seems to rule out certain explanations. Catastrophic events don't repeat on schedules. Mergers happen once. Collisions are random. Regular periodicity suggests something orbital, something cyclical, something that returns to a specific configuration repeatedly. One possibility involves a binary system, a magnetar orbiting a companion star. Maybe the companion has a dense stellar wind, material streaming off its surface. When the magnetar passes through this wind, conditions might trigger bursts. The orbital period would create the observed cycle. The geometry would determine when bursts are visible from Earth. Another idea involves precession. The magnetar's spin axis might wobble like a top. As it precesses, our viewing angle changes. Perhaps bursts only escape in certain directions. When precession points the emission toward Earth, we detect activity. When it points away, we see nothing. The cycle continues as the precession continues. Both explanations face challenges. The binary scenario requires specific conditions. The wind must be dense enough. The orbit must be aligned correctly. Precession models struggle with energy requirements. Maintaining regular bursts over months or years demands enormous power reserves. Magnetars have that power. But the mechanisms for converting magnetic energy to radio emission remain unclear. Then there's FRB 202402009A, the burst from a dead galaxy. This discovery challenges everything. Star formation regions made sense for magnetars. Young massive stars. Recent supernovae. Fresh neutron stars with extreme magnetic fields. But elliptical galaxies finished forming stars billions of years ago. Their stellar populations are old. Evolved. Nothing should be creating new magnetars. Unless the source isn't a magnetar. Or unless magnetars can persist longer than expected. Or unless the burst originated from something we haven't considered. A white dwarf merger. A black hole. An exotic object that doesn't fit existing categories. The location forces reconsideration of assumptions. It expands the range of possible explanations. What's fascinating is the distance from the galaxy center. 130,000 light-years. Most galaxies have diameters around 100,000 light-years. This burst originated in the outer halo, a region with very low stellar density. Few stars. Little gas. Minimal activity. Yet something there produced one of the universe's most energetic radio phenomena. Could the source be extragalactic? Not associated with the galaxy at all? Perhaps a foreground or background object that happens to align? Possible but unlikely. the probability of random alignment is low, and the dispersion measure fits the galaxy's distance. The evidence points to a real association, an event occurring in an unexpected environment. Each anomaly like this refines understanding. It eliminates explanations that can't accommodate new data. Science progresses not just through confirmation but through contradiction. When observations don't match predictions, something interesting is happening. Either the observations are wrong, which detailed follow-up can determine, or the theory is incomplete. Consider the long-period transients. ASCAP J 1935 plus 2148. 53.8-minute intervals. That's extraordinary. Pulsars spin rapidly. Seconds or milliseconds. White dwarfs rotate faster than that. Even slowly rotating neutron stars complete cycles in seconds. 53 minutes sits in what astronomers call the pulsar death valley, a period where standard models say detectable emission shouldn't occur. The object emits in both radio and X-ray wavelengths. That dual emission provides clues. Different energy ranges probe different physical processes. Radio emission typically involves magnetic fields and charged particles. X-rays indicate high-energy phenomena. Hot plasma. Extreme acceleration. The combination suggests a complex environment. Multiple energy sources or mechanisms operating simultaneously. One hypothesis involves a white dwarf with an unusually strong magnetic field. White dwarfs are dense but not as extreme as neutron stars. They can have long rotation periods. If a white dwarf somehow acquired a magnetar strength field, it might produce the observed emission. But that combination seems physically unlikely. Strong fields typically accompany neutron stars, not white dwarfs. Another possibility is a neutron star in a binary system. Perhaps the companion affects the emission. Maybe accretion creates the X-rays while magnetic processes generate radio waves. The long period could result from tidal locking or other orbital effects. But this still requires explaining how such a system produces regular, detectable emission. The signal from a galactic center adds another layer. ASCAP J 173608.2-321635. Highly polarized. Irregular variability. Brightness changes on timescales from days to weeks. No X-ray or optical counterpart. Similar to galactic center radio transients but not quite matching their characteristics. The galactic center is a chaotic environment. Massive black hole. Dense stellar population. Intense magnetic fields. Complex gas dynamics. Many phenomena occur there that we don't fully understand. This signal could be something known behaving strangely in extreme conditions, or something new that only appears near supermassive black holes. Polarization provides information about magnetic field geometry. High polarization indicates organized fields. Orderly structures. Not random chaos. Whatever produces this signal has a coherent magnetic environment. That coherence persists despite the surrounding turbulence. The variability pattern doesn't match any known source type. Pulsars are regular. Magnetars flare unpredictably. This object does something between those extremes. It changes on intermediate timescales. Days to weeks. Too long for typical flares. Too irregular for standard pulsations. The behavior suggests a complex system. Multiple interacting components. Processes operating on different timescales. All these signals share common features. Brief duration. High energy. Radio emission. Beyond that, diversity dominates. Different repetition patterns. Different host environments. Different associated wavelengths. The variety suggests multiple physical mechanisms. Not one explanation but several. Different phenomena producing superficially similar signals through different processes. That complexity is actually progress. Early on, astronomers hoped for a single elegant explanation. One mechanism producing all fast radio bursts. As data accumulated, that hope faded. Nature rarely offers such simplicity. Instead, we're discovering a family of related phenomena. Magnetars certainly contribute. But they're not the whole story. Other mechanisms exist. Other sources operate. The challenge now is identifying which signals come from which sources. Understanding which signal belongs to which category requires more data. Statistical analysis helps. Patterns emerge from large samples. CHIME's continuous monitoring provides that scale. Thousands of detections. Different characteristics. Clustering reveals relationships. Some bursts share properties. Similar dispersion measures. Comparable energy outputs. Consistent spectral features. Those clusters might represent distinct source populations. Different physical mechanisms producing recognizable signatures. The brightest burst ever recorded changed expectations. Burp float. Radio brightest flash of all time. March 16, 2025. NGC 4141 galaxy. 130 million light-years distant. Not particularly far by cosmic standards. But the brightness was extraordinary. Briefly outshone every radio source in its host galaxy. The CHIME outrigger array localized it precisely. Very long baseline interferometry. Multiple telescopes separated by thousands of kilometers. Combined signals pinpoint sources with incredible accuracy. They narrowed RBFLOAT's origin to 45 light-years across. Smaller than a typical star cluster. Like spotting a guitar pick from 1,000 kilometers away. Follow-up observations added crucial details. James Webb Space Telescope detected faint infrared emission from the same location. That infrared signal indicates something unusual at the source. Maybe a dense stellar environment. Perhaps ongoing star formation despite the galaxy's age. Or possibly residual heat from whatever produced the burst. Each wavelength provides different information. Radio reveals the burst itself. Infrared shows the environment. X-rays would indicate high-energy processes. Optical light might reveal stellar populations. Multi-wavelength observations construct complete pictures. RBFLOAT hasn't repeated. Scientists examined 6 years of CHIME data covering that region. Nothing. Not a single additional burst. That challenges assumptions. Many researchers believed all fast radio bursts repeat given enough observation time. The first repeater, discovered in 2012, suggested a pattern. Additional repeaters reinforced that idea. But RBFLOAT appears to be a one-time event. Unless it repeats on timescales longer than current monitoring periods. Or perhaps the repetition rate is extremely low. 1 burst per decade. Per century. We simply haven't waited long enough. The distinction between repeaters and non-repeaters matters physically. Different mechanisms might explain each type. Catastrophic events produce single bursts. Stellar collisions. Neutron star collapses. Magnetar formation. These destroy or fundamentally alter the source. Repeating bursts require persistent sources. Magnetars fit that description. They flare repeatedly over years or decades. Young, active neutron stars with unstable magnetic fields. Each instability releases energy. Some of that energy becomes radio emission. FRB 180916 demonstrated another unexpected behavior. A 16-day activity cycle. 4 days of frequent bursts. 12 days of silence. Then the pattern repeats. That regularity suggests orbital mechanics. Perhaps a neutron star in a binary system. The companion's gravity affects emission. Maybe periodically directing bursts toward Earth. Or the orbit carries the neutron star through varying density environments. Denser regions might trigger more frequent bursts. The cycle provides constraints. Whatever produces this burst must accommodate 16-day periodicity. Not all repeaters show such clear patterns. Some burst irregularly. Unpredictable intervals. Varying intensities. Those might involve more chaotic processes. Magnetic field reconfigurations happening randomly. Starquakes occurring without regular timing. Or perhaps external triggers. Interactions with surrounding material that happen sporadically. The diversity among repeaters suggests multiple subcategories exist even within that group. Fast radio bursts serve purposes beyond source identification. Their signals carry information about everything between us and them. As radio waves travel through space, they interact with free electrons. The intergalactic medium contains ionized material. Hydrogen. Helium. Trace elements. All ionized by ultraviolet radiation from galaxies. That material affects radio waves. Different frequencies travel at slightly different speeds through plasma. This creates dispersion. Lower frequencies arrive later than higher frequencies. Measuring that delay reveals the total electron content along the path. Most matter in the universe isn't in stars or galaxies. It exists in diffuse form between galaxies. The intergalactic medium. Detecting it directly is extremely difficult. Too tenuous for most observation methods. But fast radio bursts probe it naturally. Each burst samples a different path through space. Different sight lines. Different matter distributions. Collecting many bursts maps the large-scale structure. Where matter concentrates. Where voids exist. How the cosmic web arranges itself. This transforms fast radio bursts from mysteries into tools. Cosmological probes. Tests of fundamental physics. The signals experience gravitational effects. Space-time curvature from massive objects. Dark matter concentrations might leave signatures. Measuring enough bursts could constrain dark matter properties or test general relativity on cosmic scales. The bursts also sample magnetic fields. Faraday rotation affects polarized radio waves. Measuring that rotation reveals magnetic field strength and geometry throughout the universe. Current technology limits what we can learn. CHIME revolutionized the field by detecting thousands of bursts. But it can't localize most of them precisely. The outrigger array improves precision, but only for bright events. Future instruments will do better. The Square Kilometer Array, SKA, under construction in Australia and South Africa. Once operational, it will detect fast radio bursts continuously, localize them accurately, provide immediate alerts for follow-up observations. That capability changes everything. Imagine detecting a burst, localizing it within seconds, and immediately pointing other telescopes at the location. Optical telescopes capture afterglows. X-ray observatories detect high-energy emission. Radio arrays study the environment. All within minutes of the burst. That coordinated response reveals far more than any single observation. We start understanding not just what produces bursts but the complete physical context. The stellar populations nearby. The magnetic field structure. The density of surrounding material. The composition of the host galaxy. Sunbursts might never be fully explained with current physics. They might require new understanding. Unknown particles. Unexpected field configurations. Exotic matter states. That possibility excites physicists. New phenomena often reveal new physics. Pulsars led to tests of general relativity. Magnetars pushed our understanding of magnetic fields to theoretical limits. Fast radio bursts might do the same for plasma physics. Or quantum effects in extreme environments. Or something we haven't imagined yet. The WOW signal reminds us of mysteries that persist. August 15, 1977. Big Ear Radio Telescope. Ohio State University. A strong narrowband signal from Sagittarius. 30 standard deviations above background noise. It lasted 72 seconds. The full observation window. Then disappeared forever. No repetition despite extensive searches. No confirmed explanation. Natural or artificial. That signal represents the ultimate unsolved case. Perfect characteristics for extraterrestrial communication. Yet no follow-up confirmation. No context. Just one tantalizing detection. Fast radio bursts initially triggered similar speculation. Brief. Powerful. Mysterious origins. Could they be artificial? Alien civilizations signaling across the cosmos. The scientific community considered it briefly. Then evidence accumulated. Too many bursts. Too much energy. Too many different locations. The power requirements for artificial sources are absurd. A single burst releases as much energy as the sun produces in a year. Concentrating that into milliseconds requires physics beyond any conceivable technology. And doing it thousands of times from different galaxies. Nature provides more plausible explanations. But the question lingers in public consciousness. Radio signals and extraterrestrial intelligence remain culturally linked. Every mysterious detection prompts speculation. That's not entirely unreasonable. We know technological civilizations can produce radio signals. We do it constantly. If others exist, they might too. SETI continues searching for artificial signals. Narrow bandwidth. Repeating patterns. Modulation suggesting information content. Fast radio bursts don't match those criteria. Too broad. Too energetic. Too brief for complex information. The universe produces radio emission through countless natural processes. Charged particles spiraling in magnetic fields. Synchrotron radiation. Plasma instabilities. Coherent emission from pulsar magnetospheres. Shock waves in supernova remnants. Active galactic nuclei. Every mechanism follows physics we understand. Fast radio bursts fit somewhere in that landscape. We haven't pinpointed exactly where. But they don't require new fundamental physics. Just extreme applications of known processes. What we've learned is humbling. The universe operates mechanisms we're only beginning to catalog. Magnetars exist at the edge of physical possibility. Magnetic fields strong enough to distort atomic structure. Surfaces so dense that mountains rise only millimeters high. Rotation rates generating surface speeds approaching light speed. These objects seemed theoretical until we detected them. Now they're observed reality, producing phenomena that still surprise us. Each new signal class forces astronomy to expand. We thought we understood neutron stars after discovering pulsars. Then magnetars appeared. We thought we understood stellar explosions after studying supernovae. Then gamma-ray bursts revealed new extremes. We thought we understood galactic nuclei after studying quasars. Then fast radio bursts emerged from unexpected locations. The pattern continues. Nature's creativity exceeds our imagination. Our task is catching up. Building instruments that detect the unexpected. Developing theories flexible enough to accommodate surprises. The next generation of discoveries awaits. More sensitive telescopes. Broader frequency coverage. Faster data processing. Real-time localization. Automated follow-up. Every technological advance reveals phenomena we couldn't detect before. Some will fit existing frameworks. Others will demand new explanations. Fast radio bursts transition from mystery to research field in less than 2 decades. From dozens of detections to thousands. From complete uncertainty to leading hypotheses. That progression continues. We're not done learning what the universe can do. We're just beginning to listen properly. The radio universe reveals itself in stages. Each technological leap exposes phenomena hiding in plain sight. CHIME scans the sky continuously. Square kilometer array will do better. Next generation instruments will surpass both. The detection rate accelerates. Thousands of bursts. Tens of thousands. Eventually millions. Statistical analysis identifies patterns invisible in small samples. Clustering reveals relationships. Outliers highlight exceptions. Both matter. Consider what we've learned in barely 2 decades. Fast radio bursts exist. They're common. They originate across cosmic distances. Magnetars produce at least some of them. Others come from sources we haven't identified. The signals probe intergalactic space. They map invisible matter. They test cosmological models. What began as inexplicable events became scientific instruments. But the fundamental question persists. What creates signals this powerful? We have leading candidates. Magnetar surface disruptions. Crustal fractures releasing magnetic energy. Plasma shock waves in extreme magnetospheres. These explanations work for some observations. Not all. The burst from the dead galaxy challenges conventional thinking. The long-period transients defy standard models. The variability patterns suggest complexity we're still unraveling. The honest answer is we don't fully know. Partial understanding. Promising hypotheses. Mounting evidence. Not complete certainty. That's how science progresses. You identify phenomena. You gather data. You test explanations against observations. Some explanations survive. Others fail. Understanding emerges gradually through accumulating constraints. What happens next depends on technology and luck. Better detectors find fainter signals. Wider fields of view catch more events. Faster processing enables real-time response. Those capabilities are coming. SKA begins operations soon. Other facilities upgrade. The detection rate will explode. So will our ability to study individual events in detail. Luck matters because the universe doesn't schedule its performances. RBFLOAT appeared without warning. The wow signal happened once. If Big Ear hadn't been observing that exact patch of sky at that exact moment, we'd never know it occurred. How many other remarkable signals have we missed simply because no telescope was watching? How many are happening right now in directions we're not monitoring? The long-period transients hint at populations we've barely sampled. If two sources with 50-minute periods exist in our galaxy, how many exist galaxy-wide? How many in nearby galaxies? How many across the observable universe? Each discovered class of object represents a tiny fraction of the total. Selection effects bias observations toward bright, nearby, frequently repeating sources. The rare, distant, sporadic ones mostly escape detection. Fast radio bursts might be the tip of something larger. A family of phenomena sharing common physics but differing in details. Magnetar bursts are the extreme high-energy end. Long-period transients occupy a different regime. Odd radio circles represent yet another manifestation. Perhaps they're all related. Extreme magnetic fields in different configurations producing different observational signatures. Or perhaps they're completely distinct. Similar appearance. Different underlying mechanisms. The cosmos broadcasts continuously. Most signals are mundane. Background radiation. Pulsar beacons. Galactic noise. Occasionally something extraordinary appears. A burst releasing more energy than the sun generates annually. A signal repeating on precise schedules that shouldn't exist. A perfect radio circle spanning 500,000 light-years. These aren't anomalies. They're reality. The universe operating according to physics we're still learning. Somewhere in the data already collected, signals await discovery. Unusual patterns buried in noise. Weak detections dismissed as artifacts. Follow-up observations nobody thought to make. Archival searches continue revealing past events. Future analysis will find more. Each discovery refines understanding. Each measurement constrains possibilities. Progress happens through accumulation. Small advances building toward comprehensive models. The search continues because the questions demand answers. What produces these signals? How do the mechanisms work? What do they reveal about extreme physics? Can we use them to probe cosmic structure? Each question branches into more questions. Each answer suggests new investigations. That's not frustration. That's how scientific fields develop. Early confusion. Gradual pattern recognition. Eventually coherent understanding. We're somewhere in the middle of that process. Radio astronomy keeps expanding its reach. Longer wavelengths. Shorter wavelengths. Wider fields. Better sensitivity. Every improvement changes what's detectable. CHIME transformed fast radio burst science by watching continuously. SKA will transform it again through sheer collecting area and processing power. Future instruments will push further. Space-based arrays. Lunar radio telescopes. Observatories on the far side of the moon shielded from Earth's interference. Each platform enables observations impossible from ground-based sites. The universe has been broadcasting since stars first formed. 13 billion years of signals propagating through space. Most dissipated. Some continue traveling. A tiny fraction happens to intersect Earth. An even smaller fraction arrives while we're equipped to detect them. We've been listening seriously for less than a century. Radio astronomy emerged in the 1930s. Pulsars discovered in 1967. Fast radio bursts in 2007. We're still learning what's out there. What we hear changes how we understand the cosmos. Pulsars proved neutron stars exist. Magnetars demonstrated magnetic fields can reach theoretical limits. Fast radio bursts reveal transient phenomena operating at power levels we barely imagined possible. Each discovery expands the boundaries of known physics. Not by introducing new fundamental forces. By showing how known forces operate under extreme conditions we can't recreate in laboratories. The signals keep coming. Every day CHIME detects more bursts. Every week brings new data. Every month adds to the catalog. The accumulation matters. Individual detections are interesting. Large samples reveal patterns. Patterns guide theory. Theory predicts new phenomena to search for. The cycle continues. Observation. Analysis. Hypothesis. Prediction. More observation. This is how astronomy advances. Not through single breakthrough moments but through persistent investigation. Some mysteries might never fully resolve. The WOW signal probably falls in that category. Insufficient data. No repetition. Too many variables. We can speculate. We can't confirm. That's frustrating but instructive. Not every question has a definitive answer. Sometimes evidence is incomplete. Sometimes the phenomenon is genuinely unique. Sometimes we simply need better tools or more time. Fast radio bursts won't remain mysterious forever. The combination of improving technology and accumulating observations guarantees progress. We might not identify every source type immediately. We might not explain every unusual characteristic right away. But the overall picture will clarify. Leading explanations will strengthen or fall away. Consensus will emerge around mechanisms that best fit the data. That consensus might look nothing like current hypotheses. Or it might largely confirm them with refinements. Either way, we're listening. The universe broadcasts. We receive. Between transmission and reception lies everything we're trying to understand about how the cosmos works at its most extreme. The signals are real. The physics is real. The challenge is real. So is the progress. Slowly. Steadily. We're decoding what the universe has been saying all along. And there's so much more still to hear.